So, yeah, thank you. Yeah, my name is Yeon Lee, and I'm working at the Institute for Basic Science in South Korea. And thank you for the introduction, Jada. And this was the result of the really big team effort that has been conducted in 2020. And so you can see in the co-author list here. So we used the 3 spacecraft and the 6 ground-based telescope to observe Venus' day-side disk together. And as you know, that this one of the 2 major goals of this campaign was that to characterize the unknown observer that exists near the cloud top level, because it's a very, yeah, as you know, that it's a quite important source to understand the atmospheric energy balance, because it's affecting the solar heating rate so much, and we do not know its chemical composition really. So using this observational data analysis, that we expected that we probably able to characterize better about this unknown observer. So I briefly introduced that how was it the viewing geometry during this 2020 campaign. So we used a very nice observation opportunity of Bepi-Colombo. So Bepi-Colombo was on the way to, still is on the way to go to Mercury right now. And right before the first Venus flyby, there was a good opportunity to observe Venus from a distance at 0.3 AU. And at the time, Akatsuki was located between the planet and the sun. And from the Earth was able to make Venus observations as well. So using this opportunity, we used to all of our some collaborative effort using the 3 spacecraft and the 6 ground-based telescope as shown in this figure. And it was quite challenging because it was in the middle of the COVID pandemic, and we were having some restriction of visiting the site, and we could get some support from the telescope operators. And I'm showing you here about the spectral coverage of the campaign observations. So as you can see here, this slide shows that the wavelengths as on this x-axis here from UV to near infrared. And Bepi-Colombo's, the Phoebus spectrometer on board Bepi-Colombo was covering UV wavelength range. Hisaki Space Telescope covered EUV range. And as you know, the Akatsuki's UVI covered the 2 band at 283 and the 365 nanometer. And the ground-based telescopes covered longer wavelength range, which has an overlap with Akatsuki here as well. So this broad wavelength coverage was perfect to understand the unknown observer, because this unknown observer's observation spectrum supposed to be very broad. We know it's covering visible wavelength range, and it's supposed to also influential in the short wavelength range that has overlapped with SO2 gas absorption. So we wanted to understand this actually that the both SO2 gas abundance and the unknown observer, but unfortunately the Phoebus dataset turned out to have insufficient data quality for scientific observations for 3 reasons that has been described in the paper. One was at the pointing issue, one was a dark subtraction, third was about the effective area definition. So, but still we could use other data sets as shown here. I'm not going to go through all the figures, but these are the somehow summary of the campaign data sets that has been acquired successfully. And using all of those data sets, we analyzed that we compared with model calculations. So here I'm showing you very briefly about our model configurations. We used the Monte Carlo model to take into account the 3-dimensional scattering properties of the Venus disk. And for the cloud, sulfuric acid cloud, we assumed very simple the exponential cloud structures, vertical structures composed with the mode 2 and the mode 1 particles. The first in the model, we didn't include the unknown observer, but later we introduced unknown observer as a thin layer right below the cloud top level. This property was one of the best solution to fit the phase curve S365 nanometer that made of somehow fine tuning between the mid-scattering and the reduced single scattering albedo. And the right panel shows that the gaseous absorption that taken into account our modeling, that it shows as an extinction coefficient at the cloud level for all of those gases. And I'm showing you as the atmospheric Rayleigh scattering as somehow reference to understand which are the effective gaseous absorption. And here is showing the result. So all of the observations, data points are shown with the symbols or the blue curve here. And our model calculations without the unknown observer shown as a solid and the dashed line, dotted lines here. So first we used 70 kilometer cloud top altitude, but later it turned out that it was not able to fit the longer wavelength range observations. So we tuned to fit the observations, and we found that the 64 kilometer cloud top altitude was the best fitting. But this conclusion first is a bit tentative. It needs somehow more observations to understand phase curve at this long wavelength range observations. And another important thing is that the SO2 band depth, actually it shows how difficult it is using only one filter of Akatsuki. So like this one, the Akatsuki's data point is shown here, and depending on the cloud altitude, the SO2 band depths can change a lot. So we really needed the spectral data sets to understand the SO2 gas abundance. Anyway, this difference from this solid line to the observation, it indicates the impacts of the unknown observer part. So using this difference between the model calculations without unknown observer and the observations, that we could estimate absorption caused by the unknown observer. So here I'm showing you as a normalized optical depth of the unknown observer that could fit the observation most well. And first it's a optical depth, so it's vertically integrated as a function of wavelengths. So x-axis here shows the wavelengths, and the y-axis, have to be careful. It's normalized to the maximum value within this wavelength range in order to compare with other data sets, and also to be free from the cloud altitude differences. And here that our result is shown in this solid line. Yeah, this solid line here. Our result shows actually quite good consistency with the previous study taken by taken from Perez Hojos et al. During the 2007 messenger flyby, they analyzed the low latitudinal reflectivities, and this slope change around 410 nanometer seems to be consistent each other. And another important thing is that using from the comparison with the other model calculations, it seems we may need new solar heating rate calculations, because the model calculations assumption seems to be overestimated the absorption in the longer wavelength range. So here are the lessons we learned from this campaign. So we could successfully accomplish the campaign using multiple facilities almost simultaneously. And the Bepi-Colombo team, the PBOS team, precisely, now the team established how to make better observations in the future. So using the future campaign, perhaps we will be able to understand both SO2 gas abundance and the absorption by the unknown observer using the broad wavelength range coverage. And this opportunity, we are planning for a follow-up campaign in the later half of this year that will be coordinated with PBOS, Bepi-Colombo, UVI, Akatsuki, and the ground-based telescopes together. So if you are interested, please contact me. So we perhaps can discuss more about the detailed schedules together. Yeah, thank you very much.